Good day to you. This is Adam Galactic, broadcasting to you our 7th in the series in Unimetrics, the geometry of curvature. You would expect that the line is simpler than the circle. It certainly seemed so to the Greeks, and in fact it has seemed so ever since. The circle is a somewhat mysterious object because of the nature of curvature. The first step was to move the number 1 from its position on the line. It should go to the circle. Now, the nature of the circle is so fundamentally different from that of the straight line that in some ways they're opposites. We know that ratio precisely, the precision of the relationship that we have discovered, which is approximately 6.28, but there's a bit more, and it is an irrational relationship.
The number 1 never means apples.
To state the case as it
actually is.
I've been promising and promising. The quantum paradox solution.
that is called the Bošković force curve. This is a very interesting diagram. The curve is that of J.J. Thomson from a book called The Corpuscular Theory of Matter. The broken circles represent forbidden orbits. This is an orbital shell system. J.J. Thomson is one of the most famous names in the history of physics. That is the center of the atom, atomic shells, electron shells. But modern technology has provided relief for men with my affliction. Okay. So stay tuned, we'll be right back.
We'll be right back.
Good day to you. This is Adam Galactic bringing you the 7th in a series on circular geometry. We're attempting to get the geometry of light. This is a very popular way to graph an electromagnetic wave. The scale is the atomic scale. And each one of these curves, you'll see 3 small curves to the right. Those represent atomic electron shells. The inner curve, where it goes asymptotically up and disappears up, and you can see there's a reflection on the other side of the vertical median line. The opposite side is actually the spherical reflection along a certain axis. To understand this diagram, you would first need to know the meaning of the horizontal line, the vertical line, and the curved line. That, of course, is an algebraic curve. It has a formula that describes that curve. The scale and metric that describe this graph are quite interesting. This is that curve, but you can see now that instead of the vertical line, sometimes called the ordinate, we only have the abscissa, the horizontal line. Over on the far left, you will see a vertical line which is meant to cut through the center of those 4 concentric circles. This is actually taken from Theoria Philosophiae Naturalis. You may notice from this diagram that it looks similar to part of the Bošković curve. The scale here is the atomic scale. A represents the center of the atom, and the straight line going up is actually the surface of the atom. The curvy line is showing force relationship. The key to reading this is to understand the meaning of that curve. This is the diagram of a trajectory. This is also a static diagram showing a relationship that's changing along a horizontal axis. All right, that's enough gobbledygook. Now what the hell does this mean? The horizontal axis describes the flight path of an electron. This is not something that Bošković could have formulated in the words that I just used, because the electron had not been discovered yet. We just saw the picture of the man who discovered the electron, J.J. Thomson. So this is not explicitly the description of the flight of an electron toward a proton. But that turns out to be exactly what this is. So Ruđer Josip Bošković discovered the force relationship and the geometric construction of the Bohr atom over a century before any of the particles were ever discovered in science. This is the diagram of the force relationship inside the atom, and it is considered to be correct by modern physicists acquainted with quantum mechanics and acquainted with space-time relativity. This force curve is correct. This does in fact describe the relationship between the electron and the proton. And that's not all it describes. But in order to see what is being shown, what Ruđer saw, you have to realize that the vertical aspect represents force, and the median horizontal line represents zero force. Zero force. So if the electron were going straight towards the proton, it would be going on the horizontal line straight toward A. The force curve shows what happens to the electron as it approaches on a straight line trajectory. It's only traveling on the straight line. So as we travel to the left, the curve shows us the effective force. And you'll see that the attractive force increases. As the curved line goes down, the particle is accelerating. So the first part of this curve shows acceleration. So it's still being attracted, but with less and less force. When the line first crosses the horizontal axis at R, that shows no force is acting on the particle. But remember, it has a velocity. But now it goes asymptotic. And so from E up to D, that final leg going up and disappearing, that is where the electron stabilizes at a fixed radius from the proton. And so this is the stabilization of the electron around the proton. That as the electron traverses the dotted blue line, that's its physical path, the light blue line shows what the proton is doing to influence the velocity of the electron. So that's acceleration all the way to the head of the arrow. Then the acceleration starts to decrease abruptly. So now we can barely see the electron progressing on the horizontal axis past where the blue arrow is pointing exactly. Beyond where the light blue line crosses the horizontal line, the electron cannot go much further, and the light blue line indicates where that electron is in its space relationship to zero. In other words, the electron is coming to a halt. It's not going forward anymore. This entire light blue line shows forward progress, but you can see that the forward progress comes to a halt. There's no exact place where the electron stops that's visible on this graph, and it cannot be shown where the electron stops except by superimposing a hatch somewhere. The light blue line continues on to infinity without ever intersecting the vertical axis where the electron comes to stability. That is, it stops moving. Where that electron stops moving, the force of repulsion goes infinite. It's infinite repulsion. That's the meaning of the line disappearing off the top It's going to infinity, but it's not going to infinity in the spatial dimension. It's going to infinity in the force dimension. And you can see that the force dimension is perpendicular to the spatial dimension. That is exactly what I wanted you to see. There is a bit more to see, and I'm going to close this off here by pointing out to you that there are two infinities depicted on this simple graph. The two infinities are the vertical, it's actually called the asymptote. The asymptote of that vertically curving line, which defines the limit of where that curving line will never meet. The definition of the line that it will approach infinitely but will never contact, that is force. So it's infinite repulsive force. Infinite repulsive force. What does that mean? That's what we're going to discuss in the next presentation, but there is one other infinity. Look at where the curved line disappears to the right. That is also curving asymptotically with respect to the space line. In other words, that line never touches the space line. What that means is the electron, no matter how far away it is from the proton, always feels an attractive force. It's a continuous force. That's what this diagram means. There are two things you can gain from looking at this diagram. The horizontal line to the right is linear spatial infinity. The dimension to the right is spatial infinity. The infinity of space. Infinite spatial separation. There is always a force involved. So, okay, that's one aspect. There is one other infinity going vertical. That's the force infinity of repulsion. Both of these are infinite. But a force is not normally considered to have an infinite quality. So this is a relationship between force and space. We will be talking about that again so that it makes more sense. If it doesn't already make sense. If it does, that would be wonderful, but I would not expect that you would fully understand that at first blush. That's a very, very significant diagram you just saw. And I wanted you to just get a good look at it so that you would be able to have an appreciation for the geometry that you and I are developing, which actually explains this curve. So that's a brief introduction to the Bošković force curve. That is a spherical right angle. That curve describes a spherical right angle where space is converted to time and time is converted to space. Converted is, of course, the wrong word, but there is no right word. But you and I are going to develop the terminology to describe space-time the way Einstein could have described it had he known unimetrics. You will, though. This is Galactic. We'll be right back with you. Keep looking up, and we'll have more in a moment.